Uh,
A very good afternoon to all the dignitaries. My name is Chandana Dharti from Vvit Department of Vvit. A warm welcome to this session of National Level Faculty Development Program on electrical vehicles, technological advancement and trends. Today we have our chief guest, Dr. K.V. Praveen Kumar sir. Dr. K.V. Praveen Kumar sir received his BTech degree in Electrical and Electronics Engineering and his MTech degree from JNTU-K Kakinada. He completed his PhD degree from NIT Warangal. He is currently working as an assistant professor in the Department of Electrical Engineering in SVNIT Surat. He published many research papers in various reputed journals and conferences at national and international levels. Also, he is a reviewer for many reputed journals like IEEE Transactions, IET, Relay, etc. His research interests are direct torque control, predictive torque control, multi-level inverters, and open and induction motor drives electrical vehicles. Today, he is going to present the topic on electrical vehicles. Now, we would like to request Dr. K.V. Praveen Kumar sir to start this presentation.
am I audible to all of you?
Yes,
Hello.
sir.
Yes, sir.
Yes,
Yes, sir.
sir.
It is also.
Yeah. So myself, it was already introduced, so I will directly go to the topic. And today I want to focus on the PMSM drive. And before going to start the PMSM drive, let me just give you the introduction to where exactly the motor will sit and why we need this motor. So that I will first focus, and then I will go to the PMSM characteristics and how we can operate the PMSM in different modes, and what are the control strategies right now it was available in market, and suitable control techniques for the EV applications. So that is what my present agenda. If time permits, I will demonstrate one simulation study. There is a plan to hardware also, but it was not ready. It was in the laboratory. Yeah, at present day, all of we were speaking about e-mobility. The e-mobility is a basic thing in our country. We require all the transportation or everything will go on IC engines. That means right now the two-wheelers, whatever we are using till today, also we are using the same IC engine based two-wheeler applications or four-wheeler or anything. And in the recent trends, most of the cities are switching over to the e-buses, electric buses. So the e-buses are majorly with the induction motor drives. And the second thing is switched reluctance motor drive. So the permanent magnets motors are recently came into market, and also that means in the EVs, which is of a less percentage of PMSMs were used. And now the Tesla was introduced a special machine called as PM synchronous reluctance motor. So that is a one special kind of this PMSM motor only, but it will have a reluctance path creation. So it is today presentation topic is PMSM topic, and country till today we are using the IC engines. So whereas the China is using EV market and EV vehicles. So that is only the thing we should impart. And the second thing, the PMSM motors are generally not available in our country, and we have to impart that the magnets from the other countries. So that is another issue. Why the PMSMs are lacking in the EVs. So the main reason is the oil imports and also the rising environmental concerns are the major two issues for moving to e-mobility issues. And in our country, we require the electric vehicle basically due to the four major reasons. One is if you observe our traffic phenomena, like let me say simply Hyderabad or even in Guntur, like fruit market or Patna Bazaar area. So there will be huge traffic, and we have to go at the speeds of around 10 kmph or 20 kmph. We cannot move beyond 20 or 30 in Guntur roads or Hyderabad roads or in metropolitan cities also. So there the frequent accelerations, decelerations, as well as ideal condition or brakings are required. So during that condition, the preferred vehicles are EVs. So the EVs will consist of both. That means if you take EV, it will consist of only simple electric motor. Whereas if it is a IC based motor, that means combination of electric motor together with IC engine, that is called as hybrid EV. So the hybrid EV is much more suitable, even though it is a little higher in cost. So the hybrid or electric powertrains will generally operate at a higher efficiency than internal combustion engine. The second thing is a high share of energy per Indian trip is lost in terms of braking or ideal conditions. So second and third points will refer to the braking and ideal conditions. And the average range traveled in India is much smaller than the other countries. What are the other country? We know in other countries the population is less, and also uh, they have to travel the much higher distances from one city to another city or one location to other. So these are the four major constraints the EVs are preferred in our country. And also the other reasons, like we require the alternate for the oil based, fossil fuel based EVs engines, and the reduction of CO2 emissions and rapid urbanization leads to the implementation of or application of EVs into market, and also for the employment growth it is required. And now you can see here the variation of the electric vehicles from IC engine. So previously the conventional vehicles IC engines are used. Most of the motors are later on, slowly in two-wheeler applications or four-wheeler applications, slowly those were replaced with the hybrid electric vehicles. Now, today we are in the position to develop the fully electric vehicles. That is, the electric vehicle simply with its own battery system and also the battery-driven the motor system. So this is a hybridization strategy, which one from olden days to today. Yeah, the EVs are very old. Even it was there in 1920s also. Due to lack of semiconductor devices and the controlling of the AC motors is a major issue in those days. So right now we have that much advancements in the semiconductors as well as the controllers and also the communication systems. So due to these advancements, now the electric vehicle came onto the roads, and also we have seen many ongoing electric vehicles like Tata Tiago or Nexon or other types of Chevrolet motors or many things. So if we compare the EVs and hybrid electric vehicles, like the electric motor is which is 5 times more energy efficient than IC engine, and also electric vehicles are more. So even the internal combustion engine will consist of more number of mechanical moving parts, whereas the EV is consisting of very less moving parts. So that is a small comparison between EV and IC based engine. And the second thing, when we talk about with respect to the power generation and to the wheel, and also the fuel generation to the wheel. So here I just show you a simple comparison. So if we have electric vehicle, the generation will have, like if you have a thermal power plant, may have a generation efficiency of 40% and the transmission efficiency around 94 to 95%. So which gives the efficient output as 33.5%. So when it comes to the vehicle, that there will be certain DC-DC converters or internal inverters, so there will be some power loss. And finally, we may have the overall efficiency from generating station to the EV as 24.46%. And whereas coming to the IC-based engines, so we can have here refining will give higher efficiency, but it is more costly. And then transmission will give you more higher efficiency than our transmission. And lastly, here we have the pump to wheels, and the internal combustion engine is very much lower efficient, and in the pumps also there will be huge amount of petrol will be evaporated. So overall efficiency will be around 13% in case of IC based engines, whereas in case of EVs it is 24.46. The other thing, other limitation of the EVs is we have to use much number of electronic components. The decomposition or the wastage of e-components or e-waste generated by the vehicles, if we go through, if we switch over to EV, it will be very difficult thing, because if you see the IC engine roughly works for 10 to 12 years, whereas EV, based upon the battery or the motor, may work for more than 10 years. But the problem with the batteries, the battery life cycle will go beyond 5 years. We have to recycle the battery, or we have to purchase one new battery. And also the electronic equipment used in the EVs are much higher, so that is another limitation. So these are some limitations for the EVs also still exist. Here a small comparison was shown between electrical versus gasoline engine. So in case of electric cars, we use tailpipe emissions are very less, and utility company will produce very less amount of green amount gases, or also the charges of electricity was less compared to Organization of Petroleum Exporting Countries. That means it involves all refining and fixing of the cost of the oil. So it will be little bit like refining only will charge much higher. So at present we know the Russia is giving much barrels of oil to us, but the cost of oil was not reducing, because the oil the refinings all are private based refineries, and also we have certain amount of taxes. So that is also another limitation right now. Even though we are importing much amount of oil from the other countries, but the cost will not come down. That is another reason. So we have to switch over. So that is why comparison was made here. And also miles range are a little lesser in case of electric vehicles, because if you want to travel much higher distance, you have to use a battery of higher capacity. And the limitation, another limitation is fuel can be filled in minutes or seconds, whereas electric vehicle the charging time will be much higher. So that's why we are shifting for the fast charging stations, which may be compatible to charge in 15 to 10 minutes. So overall, the electric vehicle is simply consisting of electric motor or IC engine. So if it is having both electric motor or IC engine, then it is called as hybrid electric vehicle. So instead of the batteries, if we use a fuel cell, then it is called as fuel cell electric vehicle. So based upon the EV, there will be specific design aspects, as well as the same core electrical technology it will require. So the term EV, just to prefix that, the propulsion system used is electric motor. So if you use only the electric motor as the propulsion system, then it is called as simply EV. If we use both the combination of electric motor as well as IC engine, then we will call it as hybrid electric vehicle based upon the storage. If we are using a battery or a fuel cell storage, then we will name it. We will generally call it as fuel cell EVs or battery EVs. And it is a simple battery based EV. So in case of battery based EV, it is a fully electric vehicle, I can say, because the battery charging was there, or batteries were installed inside the EV, and we will place the rechargeable batteries. So generally the battery packs are, usually we use very high capacity battery packs, and their battery power is used to run for the longer distances. And also we use onboard electronics with the help of same battery supply, and they do not emit any harmful emissions or hazards. So this is simple battery electric vehicle, and there are other classifications. So the stages of electrification was shown. In case of conventional vehicles, there was no any electrification. Only the batteries are used for simply lightings, or like making alarms or buzzering. The second thing is a hybrid electric vehicle. So in case of hybrid electric vehicle, we are going to use both the motor as well as engine. So here the battery will drive the motor and the fuel will drive the engine, and the transmission will be depends upon whether the configuration, whether it is a series or parallel or hybrid, that means series parallel. So based upon that, the transmission will be used. And this third one is battery EV and fuel cell EV. As I told, in case of electric vehicle, we are going to use only the motor, which was fed by a battery. Whereas in case of fuel cell EV, also same thing. The motor will, we are going to use some simple a fuel cell based EV, like air compression will be there, and fuel cell will convert that gases, the fuel gases or H2O into hydrogen gases into the voltage, and the voltage will be stored at the battery, and the battery will driven through some power control unit. So this is used in a Toyota a fuel cell Toyota car. So these are the simple stages of electrification. So the electrification is used in case of hybrid vehicles or battery vehicles or fuel cell based vehicles. And this is a typical block diagram of overall plug-in battery electric vehicle. So here the front side, this means this front side will talks about how the grid is interfaced to the charging environment. That means here on-board charger we will use. That means on-board charger will be directly connected to level 1 or level 2 or level 3 charger station. So level 1 charger station is 1 to 120 volt AC. Level 2 charger station 1.3 to 240 volts AC. Level 3 is like AC/DC based upon the requirement of the vehicle. So these are the 3 different types of charging stations are generally used in present days. So in case of level 1 charging station, so we'll directly plug to the level 1 charger directly. So on board charger there will be different types of chargers like PFC converters or LLC converters. There are many classifications of on board chargers. It is simply a combination of a DC-DC converter with the elements, energy storage elements, or I can say inductor and capacitive combination of connections. So here we will use initially AC to DC conversion. Rectification has been done. After rectification, we are going to use DC-DC converter. That DC-DC converter will send the output voltage as a constant DC. That constant DC will drives the inverter. Will drives the inverter. Here I can say this is a traction drive. In the traction drive, you have the energy through external source as well as the battery pack. So here the battery pack, whenever it is needed or when the external supply was connected or in the ideal condition or in the braking condition. So here we will generally use a bidirectional converter. The bidirectional converter will store the battery in the conditions like when it is connected to charger. In the second condition, when the motor is operating in the braking mode, or when the motor is in the ideal condition. So in those conditions, battery pack will be stored through bidirectional DC-DC converter. Or in the normal conditions, if the external charger was not connected, that means external supply was not available, then the battery will drive the inverter and the motor. So and the other loads like lights, like horns, heaters. So all those things will be driven by a unidirectional DC-DC converter. So like LED lights or internal sound systems or whatever the internal existing things, those will be driven with the unidirectional DC to DC converter. So my major portion is this motor part and this motor control part. So motor control part will be done with the help of this inverter. So the inverter operation and the motor control part is today's my contribution in terms of EVs. So basically, there was huge amount of research is going on. One in terms of the charging units, that means the onboard charger, and also the charging station. Like from the grid and nearby your roadside, there should be a EV charger. So that EV charger, still fast charger or ultra fast chargers are required because we do not have much time to charging the EV right now. So we require fast chargers or ultra fast chargers. And onboard chargers also, right now we are having the efficiencies around 85 to 90% mostly. So still the researchers are working on this onboard charger, and then the other things are motors. So motor control. So this is one thing, and based upon this, we have integration or vehicle to grid integration or vehicle to grid technologies. Many things were there. So those are also under the one of the area of the research. Yeah. So this is what I told. This is from the external supply, and if we have internal sources, different types of sources. battery, supercapacitor, fuel cell. If we have many number of sources on board itself, that means in the EV itself, then we can manage these three sources according to our requirement. Generally, the batteries will supply whenever the battery is uh, less charged or DC link is unable to maintain by the or a DC link voltage required by the motor, or the amount of power required by the motor is not able to maintain by battery, then the fuel cell and supercapacitors can be an alternate solution. So this is another view of an EV, which is on-board storage is present. Next one, yeah, this is a overall block diagram. So this is a simple block diagram which shows the wheels and all things. So here my major part is on motor drive and its controller. So I'm not going to master control and DC-DC converter. So I'll just go through the motor drives. So we know the basics of drives. An electric drive is simply nothing but a drive is called as simply a system which was employed for motion control. So that is called as a drive. So for the motion control, if we employ a diesel or prime movers, then those are called as normal mechanical drives or drives. So if the drive employs an electric motor, then we will call it as electric drive. So there are different types of electric motors. One is called as DC motor and the other one is called as AC motors. In case of DC motors, we require regular maintenance and those are of heavy in size, expensive. So due to several limitations, due to the brushes are not easy to operate them in like hazardous environments. Whereas in case of AC motors, they are require less maintenance because they do not use any commutator or brush segments, and also they can be used for the longer times of duration, light and less expensive. They are also used for the high speeds of operation, and the coupling between the torque and flux is required in case of AC motors. Whereas in case of DC motor, if you take a separately like DC motor, there exists always decoupling between the stator flux and the rotor field, or I can say the stator current and the rotor fluxes. So there will not be any control. That means the rotor can be energized. That means armature can be energized through a supply, and the field can be separately excited. Whereas in case of AC motor, the both were interlinked. So the transformations were much helpful to make the AC motors are decoupling of the stator and rotor quantities. So the overview of AC drives. So in case of AC drives, before the 1950s, mostly the DC motors are used for the variable speed applications, and later on the advent of semiconductor devices or the implementation of the inverter control strategies, so made use of these AC motor drives for variable speed applications. So till 1950s, DC motors are the market role. So later on, that is in 1980s almost. So in 1980s, the AC motors are used in high performance applications like lifts, tractions, servos, and the AC motors became much good alternative for the DC motors. But the control of AC motors is a little bit complex, and also the control requirements is a little bit expensive. Whereas in case of DC motor, the control is very much easy, and the device available also very cheaper in cost. And when come to the controlling side, if you observe the DC motor torque equation, the DC motor torque equation simply consists of T is equal to K phi into IA. So simply we have flux. The flux will be generated from the field. That means I told you there exists in DC motor stator as a field and rotor as armature. For the rotor, rotor is simply armature. The armature current is IA and stator field is lambda F or xi. So in case of DC motor, the torque equation simply depend upon flux and IA. Whereas in case of induction motor and synchronous motor, we do not have a single winding. We will have multi-phase windings like three-phase windings or polyphase windings. So if we have a polyphase winding, then the torque equation will depends upon the stator variables psi A, psi B, psi C, as well as rotor variables psi RA, psi RA, psi RA, psi RB, psi RC, and also the angle between them, the stator and rotor. So in case of synchronous motors, there exist almost 7 variables in the torque equation, 7 variables to be controlled in the torque equation. Whereas in case of DC motor, only 2 variables we require. so which can be controlled very easily. And both are also independent of each other. Whereas in case of the induction and synchronous motors, the stator and rotor parameters are interlinked. So the overview of AC drives, I told you, before 1980s, there was no much implementation of the motor drives in terms of vehicles for closed loop applications. Later on, only it was much higher importance were given in terms of the invention of the field-oriented control. Later on, the space vector modulation. So due to these two techniques, many further advancements were happened. Direct arc control, and then in the recent days, the predictive control is one alternate. So these are the various control techniques which were used till 1990s. So field oriented control, direct arc control, DTC with space vector modulation, and also ANN was also applied to the motor drives in 1990s itself. So now this slide shows the different types of electrical drives. So here I told initially DC motors are olden days it was used. At present days we are using the AC motors. And the AC motors are classified into three different types. One is a synchronous type, variable reluctance type, and asynchronous reluctance type. So asynchronous motors are called as induction motors, and they are also of squirrel case and wound rotors for high power applications like bus applications or tram car applications. So in those applications, preferable motor is induction motor due to its high power carrying capacity, and also due to the other features of the induction motors. Whereas in case of two-wheeler or low power applications, the preferable motor is a BLDC motor, and it is not preferred for the high power applications because of its stator current limitation. The stator current is always a quasi square current it will take, so the harmonics will be very high in case of quasi square current. Whereas in case of the other motors like synchronous motors, other classification is sinusoidal motors, that is called as permanent magnet synchronous motors. In case of PMSM also there exist two classifications. One is internal PMSM, one surface PMSM. For lower speed applications, due to the rotor saliency, the surface PMSM is preferred for lower speed applications, whereas for the higher speed applications it is preferred to use internal mounted PMSM. And also the relation between the direct and quadrature inductances are very much higher in case of IPMSM, whereas LD is nearly equal in case of surface mounted PMSM. So preferably IPMSMs are much mechanically stronger and also mechanically robust. That is why IPMSM is more preferred than SPMSM motors. So here this slide shows simple application of AC drives in different areas. So one is induction motor drives. The induction motor drives are called as normal electric motor drive only. So the other motors like PMSM, BLDC, SRM drives are called as special machines. So, and these special machines does not have any rotor coil. So simply they will have rotor as iron bar or magnets on the rotor. Whereas in case of induction motor, the stator and rotor both will consist of a winding on it. And as I told, the switched reluctance motors are highly used, and induction motors are used for the high power applications. The PMSMs are less preferred till today also due to the non-availability of the permanent magnets in the market, but it is more advantageous than other types of motors. So that is why the recent Tesla launched permanent magnet assisted synchronous reluctance motors. It is a type of reluctance motor only, but it uses the permanent magnets on the rotor, which will add the magnetic flux onto the rotor so that higher amount of flux densities with the lower power capabilities can be easily obtained with the help of PMSM synchronous reluctance motors. Now, if you talk about the electric drive, so basically there exist different types of challenges we have to face in the electric drives. First one is we require very high response and torque accuracy. The second one is the developed control strategy should be much highly reliable. The third one is low speed and high accuracy sensorless control, because every time we may not prefer the sensored control, so we may need to go for the estimators or the other mechanisms which does not use the sensors. That means at least speed sensor we need to try to avoid, because the speed sensor will generate always the ripple content when it was synchronized to your the shaft of the rotor, because we are going to use an encoder which generates the number of pulses per rotation. That means if we have a higher number of pulses per one rotation, it will generate that lesser amount of ripple at the output. But even though it is a lesser, but it will generate the like more deviations until if we use a filter. So the output of encoder, generally we will connect a filter, thereby the higher order frequency or simply eliminate by using the filters. Because if we are operating at this lower speeds, the higher order harmonics will makes the more acoustic noise into that low range frequency or speed signals, and then large capacity is required in high power applications. Those can be easily obtained by the multi-level inverter. So right now there was huge amount of research has been already developed in the area of multi-level inverters. In addition to the dominant topologies we known to us, NPC or diode clamped or cascade distribution inverters. The next one is downsizing and efficiency. It depends upon the selection of your inverter and also its switching strategy. The last one is high-speed machines and operation. So high-speed machines are generally used in case of EV purposes only. And the second thing is their control is also a little bit tough challenging, because we have to operate the motor in order to get the motor into the very high speed range, we have to operate it in flux weakening. So in the flux weakening, we have the other control strategies. So I told that permanent magnet synchronous motor is a very important motor, and it has certain good characteristics than other motors. Will operate at higher power densities compared to the induction motor, or it does not require any rotor current, so that the current taken by the stator will be less as compared to the induction motor. So it will operate at good power factors than induction motor or other types of motors. So due to the advantages of the permanent magnet synchronous motors compared to other motors, it is a one important motor in the EVs. So, and second thing, when we are selecting the permanent magnet synchronous motor, we have to see its characteristics. The characteristics or its design or the internal parts of the PMSM. So, if we consider the stator part will be a simple winding in nature. So, there will exist two types of winding framed on the stator. Based upon the winding nature, the induced EMF will be developed. The induced EMF will be responsible for the generation of the flux in the stator. And the second thing is in case of the PMSM motors, we use the permanent magnets. And the permanent magnets are made up of different types of materials like alnico, ferromagnets, nickel cobalt combination, or cobalt neodymium iron boron combination, or samarium cobalt combination. So there are different types of the permanent magnets are available in market. So one basic magnet is alnico magnet. The alnico magnet, the characteristics of magnets were shown here. So the alnico magnet was shown with a line like this. The alnico magnet is preferred only for the electromechanical instruments, not preferably used in case of permanent magnet machines, even though it has a very high residual flux and also a very strong flux density, it is not preferred. So I told in case of motors, we require the motor has to operate in the flux weakening mode so that it will go to the high speed of operation. Like in case of DC motor also, we have two phenomena called as armature control and field control. So if we operate the motor in the field control region, we'll reach the higher speeds of operation. That means above the base speeds of operation. If it is below the base speed, we'll generally control the armature current. Similar way, the alnico material will offer a very strong flux density, so that we will have always a higher rating or higher size, bulk size magnets in case of PMSMs. Second thing is it should have higher value of the product of BR into H. So the residual flux, and if you observe here from this graph, the alnico has high value of Br, but it has a lower value of H. Whereas coming to this line, this is a neodymium iron boron combination. This neodymium iron boron combination is available with higher flux density as well as higher magnetic field intensity. So the B versus H characteristic is almost linear in case of neodymium iron boron combination, whereas in case of it is non-linear for alnico materials. And the other things are like the recoil permeability or recoil line, and the rare earth magnets. The rare earth magnets are simply samarium cobalt or neodymium boron combination. So those are called as rare earth magnets. So here the different types of magnets were shown. Out of these different types of magnets, I told simply about alnico and neodymium iron boron. So preferably neodymium iron boron combination is used in the PMSM motors, and it is less available in our country. And I told you, based upon the stator winding, there are two types of permanent magnet motors are available. One is called as permanent magnet synchronous motor. Second one is brushless DC motor. So in case of the permanent magnet synchronous motor, the stator windings are distributed and they will always generate the sinusoidal EMF as shown in this bottom figure. And we will generally give the constant torque simply obtained by giving a sinusoidal current. Whereas in case of BLDC motor, as the stator winding is concentrated in nature, we have to give a square amount of current. That means quasi-square waveform is generally preferred to generate a constant torque. So the generation of this constant torque in BLDC require a square waveform current. So this square wave currents generally will have higher amount of lower order harmonics, which require huge filter designs, and also the power handling capability is also less in case of the BLDC machines. So that is why for high power applications, preferable motor is PMSM. For lower power applications, less than, I can say 2 kilowatt or 3 kilowatt, preferably we can go for the BLDC motors, which will be suitable in case of suppose 100 kilogram or like 100 kg or 50 kg can be easily driven by BLDC motors. For more than 100 kgs or any other higher weight applications, preferable motor is PMSM. So up to 100 kg or 150 kg, we can see electric bikes. So the most of the electric bikes, two-wheelers are employed with e-bicycles also. Bicycles also employed with BLDC motors only. So in case of that bicycles, there will be hub motor. The hub motor will be driven by the inverter. So this is a simple differences between the BLDC motor and PMSM. Both are synchronous machines, and BLDC will be fed with inverter with a different switching combination than the PMSM with all three legs are going to be functional in case of PMSM, whereas in case of BLDC only two legs are in the functional mode, and it will generate the trapezoidal back EMF. In PMSM there is a sinusoidal back EMF, and also the flux position commutation is required for each 60 degrees, but in case of continuous stator flux variation is obtained. So as I told, only two phases will be on. Here all the three phases will be on. Torque ripple is having much higher commutations. There will not be any commutation torque ripple in case of PMSM. So I told there are many advantages of the PMSM, like it has high torque to inertia ratio, high power density, high power factor, high efficiency, and it has compact structure, excellent dynamic properties, etc. So due to these all advantages, the PMSM is replacing many of the induction motors, even for the medium power application and also in high power applications. For low power applications, preferable motor is BLDC motor, even though it has some other irrelevant characteristics, but the preferable motor is BLDC motor. Even though it is having higher torque ripple or acoustic noise is easily generated by the BLDC motor. And even the BLDC motors are preferred in our motherboards, the desktop motherboards. So now let us start the PMSM control strategies. So it was having high torque, high power density, and also efficient and good dynamic response it will give. It was preferred in industrial applications also, along with EV or domestic applications. In case of PMSM, the rotor is completely made up of the permanent magnets. So the rotor does not require any external supply. As the rotor does not require any external supply, the field, the permanent magnet flux will be a constant value. And generally, the PMSMs are operated with the help of voltage source inverters. Variables for variable speed operations, we have to operate the PMSM with voltage source inverter only, and the PMSM will generally have a distributed winding, and it also fed by the variable frequency, variable voltage, or variable current sources. And the permanent magnets were placed on the rotor, so it will eliminate the losses caused by the field winding. Also, an additional supply requirement or the commutator brushes or slip rings, everything will be replaced. Everything will not be used in case of PMSM motor. So simply the rotor part will be replaced with the permanent magnets. And in case of the conventional synchronous motors, the power factor can be easily controlled by controlling the field current. Whereas in case of PMSM, the controlling of power factor is a little bit difficult, because you have to always concentrate on your stator current component, and the stator current component will be decomposed into the flux generating component and that means ID and IQ, or I can say the quadrature and imaginary, the quadrature and real components of the stator current. So the power factor control is a little bit difficult in case of PMSM. The power factor control can be possible only with the help of your stator current only. Whereas in case of induction motor or the synchronous motors, in the case of induction motor also it is possible through your stator current. Whereas for the synchronous motors, the power factor control can be done with the help of field excitation. So this is a difference between the PMSM and conventional synchronous motor. So there are various classifications of the PMSM based upon the location of the permanent magnets. So in case of surface mounted permanent magnet motors, the magnets are placed on the surface. So it will have less mechanical robustness. That is why it is preferred for low speed applications only. And the variation of the quadrature and in direct axis inductance is also nearly same. Whereas in case of surface inset PMSM and interior PMSMs, the ratio of LD and LQ was very high, so that it will give higher amount of torque, and also higher amount of speeds can be possible by using these motors. And the construction wise also, the magnets are placed interior to the rotor surface, so it will operate at higher speeds. So before going to the control strategies of the PMSM, it is preferable to understand its phasor diagram or its control techniques. So if we see the stator part is simply consisting of a winding which is generating the magnetic flux. So the stator part can be simply represented in terms of a Thevenin equivalent circuit or a Norton equivalent circuit. For simplicity purpose, I am considering the stator part as by application of the Norton equivalent circuit. That means a current source in parallel with inductance, because I'm generating the flux from the stator coil. So the stator is consisting of a coil and it has a variable current source, let me suppose. And the magnetic field is generated by the permanent magnets. So in order to have the magnetic field of the permanent magnets, I'm assuming that the magnetic field is also I'm just taking the assumption the field is also created with the help of some current source. Even you are not using the current source, just for the assumption purpose, I'm taking it as a current source. For the stator part, I'm applying Norton equivalent source. So on showing the Norton equivalent circuit, so here IS and IM, this is a current flowing through the IM, and IF is a field current. So the flux was generated by the permanent magnet was represented with the help of an equivalent source IF, and these two are the stator equivalent Norton circuit. And the phasor diagram will be drawn by taking the reference phasor as IS. So if IS is reference phasor, the voltage developed across the coil will be lagging by an angle. And the second thing is, so here I am assuming that IF is a permanent magnet flux. The permanent magnet flux and the EMF, induced EMF, will always have an angle of 90 degree. So this angle, induced EMF and IF will have 90 degree. The stator current is decomposed into the current flowing through the coil and the field current. So IS is composed of IF and IM. IF and IM. So here IM is simply you can call it as the IF is a current which will be in terms of your rotor flux. So I'm decomposing the IS current in terms of the field current and the torque current. That means flux producing component of current and torque producing component of current. I will discuss you in the next coming slides. So just I'm showing here IM is equal to IS plus IF. So the mechanical power developed across the motor terminals can be, or the mechanical power developed by the shaft of the motor can be written as a PM equal to 3 EIS cos of delta minus pi by 2. When we are writing the mechanical power, we will take in terms of the induced EMF E. So 3 EIS cos of delta minus pi by 2. And here, if you have the value of cos delta minus pi 2, you can write it as sine delta, and E can be written as the induced EMF can be written in terms of, with respect to flux, you can write it as the reactance excess into IS, I can write. So the mechanical power developed can be depends upon the 3 XS IF sine delta. So we know P is equal to omega t. So from the relation of P is equal to omega t, the torque can be written as P by omega. So the torque equation simply can be written as K into IF sine delta. So if we observe this torque equation, so here I have IS and IF. So IS is called as stator current component. IF is a proportional component of rotor flux. It is not exactly the current flowing through the rotor. So we are just having the assumptions only. And the torque will be maximum when delta is equal to 90. So here the value of, for a given value of IS, the maximum torque can be obtained when delta is equal to 90. So the PMSM can operate only when the value of the stator and the field currents are exactly in quadrature. That means, as we see in case of the DC motor also, the flux and IA component should be perpendicular to each other. In the similar way, IS and IF should maintain an angle of 90 degree. Then you can have, that means when I say IS and IF are 90 degree, the angle between E and IF, E and IS should be in phase. So if IF and IS are in quadrature, then the motor will operate at maximum torque. So the maximum torque can be easily obtained by imposing the stator current component in such a way that IS is exactly in quadrature with field current IF. So the IS is the stator current which was feeding by my inverter or any other variable current source. So the IS is in the hands of the user. So the IS can be controlled. If the IS is controlled, the angle between IS and IF will be controlled, and hence maximum torque can be easily obtained. So as the motor will have the simply the stator winding, the rotor is not at all rotor parameters are not at all in your hand to control. So it will always operate in the lagging power factor mode. The motor, it will always operate in the lagging power factor mode. And if you make delta is equal to 90, you can get maximum torque per ampere control. That means T upon IS will be a maximum value. And third one is, in all the cases, we may need to operate the motor in the braking condition also. The braking condition, the current will be generated by your motor. So under braking condition, the value of delta, the current value, IS will be returned. IS will be a negative sign. So in that condition, delta is equal to minus 90, which will sends the power from the PM permanent magnet machine to the inverter terminals, and a bidirectional converter will be used to store the excess power which was generated by the motor under the braking conditions or ideal conditions. So to operate the PMSM in maximum torque condition, the value of angle between IS and IF should be 90 degree. And in the flux weakening mode, the value of delta should be more than 90. So when delta is more than 90, the stator flux component will have two components. One is called as quadrature component, and the second one is called as a direct component. one in quadrature with IF and the other is in opposition with IF. So this IS can be decomposed into the torque producing component and field producing component. So uh, what are the component when it is greater than 90? So I will show here. For this IS component, you can decompose into one component in terms of the quadrature, one component in terms of opposition with IF. So for delta greater than 90, that means the angle between IS and IF is greater than 90, then it is possible to operate the PMSM in flux weakening mode. So when the motor is went into flux weakening mode, then it is easy to operate for the higher speeds of operation. So I want to reduce the field component. In order to reduce the field component, I'm assuming that the IF and IS are the corresponding components, and these are all for analysis purpose. And usually what we'll do is IF is a uh, d-axis current we'll suppose. So IM is a torque producing component of current. So based upon this torque producing component of current, and that means ID and IQ will generate. The ID is proportional to IF, IT will be proportional to the IQ. So we just focus on the angle between these two. And if we want to operate in the flux weakening mode, we will ensure that the IF is having one phase opposition component. That means we are going to inject a negative component of small component of current to reduce the flux of the PMSM. So that is how you can operate PMSM in the flux weakening mode, by making IS and IF angle is delta more than 90°. And for the control of motor, it is better to, even it is for FOC, DTC or predictive control or any sensorless control, we require mathematical model of the PMSM. The mathematical model of the PMSM will makes the decoupling of air gap flux and torque in the drive system, so that the torque and flux components are decoupled. That means the torque producing component of current and the flux producing component of current can be easily decoupled by applying mathematical transformation like Park transformation, or simply applying the rotating reference frame or synchronous reference frames. So in case of PMSM, the rotor will rotate at the synchronous speed, so you need not to worry about that. That's why simply you can have a synchronous reference frame. The two-axis PMSM stator windings can be considered to have equal number of turns per phase. The rotor flux can be assumed to be having two components, D component and Q component. And generally along the Q component, it will be zero. Along Q component will consider when we require a flux weakening operation, or the amount of flux is in the D axis only. And the rotor flux is assumed to be constant under normal conditions. And even if there is a temperature variations, the temperature variations will be assumed to be negligible. And the equations of the, here I'm showing the final equations of PMSM model. So it require VQS, VDS. The VQS, VDS are the D-axis and Q-axis voltages of the PMSM, which will be obtained from the transformation of the voltages applied to the stator. VAVC were converted into VQS and VDS. Lambda QS and lambda DS indicates the Q-axis and rotor Q-axis and D-axis rotor flux, and which will be decomposed in terms of the stator and the rotor components. Lambda QS can be written as LS IQS, LM IQR, and similarly lambda DS can be written as LS IDS and LM IDR. And generally lambda DS we will consider, lambda QS can be made as a small value or nearly zero. So if you write these equations in the matrix form, then we are going to get VQS VDS equal to RQ plus LQP omega RLD minus omega RLQ, RD plus LDP, IQS IDS. And the torque equation is a general equation which will be depends upon the stator current as well as the rotor flux. So from those two, we can write this torque equation in terms of DQ components as 3 by 2 P by 2 lambda ds IQS minus lambda QS IDS. So these are the required components for the torque. So let me show you the dynamic model of the PMSM. So I think my screen is visible. So here we are separated into different forms. So I have VA, VB, VC. So these VA, VB, VC are generated from the inverter. So this is my mathematical model of the inverter. So from the inverter, we are developing the phase voltages VA, VB, VC, and these VA, VB, VC are converted into VDS, VQS by applying Park transformation. I'm not giving the equations. I'm just telling Park transformation. So VA, VB, VC converted into VD into VD, VQ, and these VD, VQ are the inputs. And as we know the equations, VD, VQ is equal to VD is equal to this equation and VQ equal to RQ plus LQP, RQ IQS plus LQP IQS plus omega R LD IDS. From this, as I know the voltage which was obtained from the inverter terminals ABC and VD, VQ are known to me, on subtracting VD minus RDID plus omega R lambda Q will be d lambda by dt. So the output of this adder. So here I am adding VD and omega R lambda Q minus ID into RS, so that I will get here d lambda by dt. That means lambda d by dt, rate of change of lambda d by dt I will get. So on applying integration, I am going to get the flux. So this I will get lambda ds I will get. This lambda ds is a composite of LMIFR plus LMI, that means LMIDR plus LSIDS. So from this I can get IDS. This IDS will be fed back to here. So in this way, we are generating the IDS, lambda QS, lambda DS, IQS, lambda QS. So if once we have generated these all required components of the torque component require lambda ds IQS, lambda QR IDS. So we will generate lambda ds IQS, lambda QS IDR by using the stator, that means VQS and VDS. From the values of VQS and VDS, that means the voltages which are going to the motor terminals, ABC voltages, are converted into VQVD. As VQVD were known to us, we are estimating lambda Q, lambda D. Once lambda Q, lambda D were known, you can estimate the currents also. So this is a simple mathematical modeling in MATLAB simulation. So once IDIQ, lambda D, lambda Q were known, then we'll use the mathematical model of the PMSM motor in the rotor side. That means these all I have talked with respect to stator. So the rotor has generated the flux and it will have a torque component. So the torque component will be generated by using 3 by 2 P by 2 lambda D, this component lambda D IQ minus lambda Q ID was subtracted and generated the component MD. MD means torque. 3 by 2 P by 2 here, MD. I have got electromagnetic torque. And this electromagnetic torque will be subtracted from the load torque. And this equation is simply TD is equal to TL plus J d omega by dt plus B omega. That would not show generally. This is a second order torque equation, which we'll study for the rotational systems in your control systems also. And the further equations are the torque equation can also be written in terms of 3 by 2 P by 2 lambda A IQ plus LD minus LQ into IQ ID. So the first equation will be used for SPMSM or IPMSM. So when you are specifically using IPMSM, it is better to go with the second equation, 3 by 2 P by 2 lambda IQ plus LD minus LQ into IQ ID. And the definitions of the LQ, LD and are shown here. LD and LQ are given here. I'm not discussing LD, LQ separately because so these are the modeling of PMSM. And in order to implement the FOC, there are two types of field-oriented control was there. One is direct FOC and the other one is indirect FOC. The direct FOC is nothing but the theta angle, the rotor angle is obtained by using flux sensing devices, which were embedded inside the motor terminals. Then it is called as direct FOC. If the value of theta f, if theta f was obtained from the integration of the rotor speed, then it is called as indirect FOC. So in case of the induction motor application, in addition to the rotor speed, you have to add the slip speed. Then you are going to get the value of theta f. That is why here omega SL was shown as addition. So as we know the mathematical model, now it is easy to develop the vector control. So I have shown all these equations. So these all are the mathematical model of the PMSM. So in this mathematical model, the torque derivation was shown here. T is equal to 3 by 2 P by 2 LD minus LQ ID IQ plus LMD IFR IQR. So I have a IPMSM motor, so that's why we use a torque equation this one. So the first term will show the reluctance torque and the second one will show the field torque. So I have the addition of torque component. Reluctance torque is adding to my the field torque. The field torque is nothing but as in your DC motors, you will have only the field torque. That means field flux and field current will generate the field torque. Whereas in PMSM, in addition to field torque, there will be additional term called as reluctance torque. So higher torque can be easily obtained in case of the PMSM machines compared to the DC machines also. So for the vector control of PMSM, just now I told you the stator current component will be decomposed of two components. One is a D-axis current component and the Q-axis current component. The Q-axis current component, that IM component, the IM component is called as Q-axis current component, or IT I'm writing. So this IT is called as the torque producing current component, and the IS component is this component is called as field current component. So IF is IS cos delta dash, which can be written as, this is a simple right angle triangle, so you can apply how to determine IT and IF. IT is IS sin delta and IF is IS cos delta. So if you substitute IQS and IDS in this equation, you will get the final equation as T is equal to 3 by 2 P by 2 LMD IFR IS. So this equation is looking like a simple DC machine equation. So up to this part, you have dependency of stator and rotor variables. So here you have the PMSM equation 3 by 2 P by 2 LMD IFR IS. So where IFR stands for the field current and IS stands for the stator current. So the stator current will have the two components, field current component and the torque current component. And this field current and torque current component will vary based upon the stator current angle. So if you have an angle in between IS and IF is 90 degree, then you can have maximum torque. Otherwise, it will operate at the other torques. So the general equations of the PMSM I already discussed to you. So in order to obtain the maximum torque, we have to operate the PMSM with an angle of IS and IF as delta is equal to pi by 2. Then you can achieve maximum torque per ampere control. So in addition to this, there are many other modes also: unity power factor control, MTPA control, and also ID is equal to 0 control. So many control mechanisms were there. So here I'm just showing the FOC and then predictive current control in short. So this is an overall block diagram of the field oriented control of PMSM. So here I will just come from the motor side. So from the motor side, I am measuring the speed. The measured speed is given through a signal conditioning circuit and given as a feedback to the reference signal. The reference signal may be given by the varying of your gear mechanism of your EV system. And the speed comparator will generate the error. That error is given to the speed PI controller, which generates the torque reference. The torque reference will be multiplied with the f of omega bm component in order to have the constant torque or variable torque. So for the speeds less than base speed. So here f of omega bm was defined. F of omega bm equal to omega b by omega m. When you are operating the omega m, the motor speed was above the base speed and the less than maximum speed. So above base speed and less than maximum speed. And the second one, this f of omega bm will be equal to 1 when the base speed is less than motor speed. So the DE star will be same as T star for the values of f of omega bm is 1, and it will be a little decrement when you have f of omega bm is omega bm by omega b by omega m. Simply you have to generate a lookup table or function. The function is simply consisting of comparison between your omega B and omega M. So if omega M is less than omega B, then the output will be 1. If omega M is more than omega B, your output will be decreasing in nature in the manner of omega B upon omega M. So this will be multiplied with your torque so that you can operate in the constant torque mode or variable torque mode. Constant torque mode or constant power mode. So here the equations were shown here. PA is equal to omega M TE, where TE is a function of omega BM. So here it was shown omega M F omega M omega BM T star. So when T star, that means this is 1, PA is equal to omega M T star. So torque as T star is same as T star is same as T star. You can have motor operation in constant torque mode. And if T star is a variable, then you will enter into the constant power mode. So for a PMSM also, you can define in terms of for the speeds less than base speeds, the torque value will be maintained as constant. So it is called as constant torque mode. And simply you are operating the machine in the constant flux mode. The second thing is the TE star will be given to a function. So here T is equal to 3 by 2 P by 2 lambda AF IS. So from this I can have the torque component and the flux component. TE depend upon TE upon K1 lambda F will give you IT. T upon K lambda F will give you IT. And F of omega BM into KF will give you IF star. That means here also another function generator is used. The function generator will operate this function generator will generate the constant amount of current up to the value of base speed. Beyond the base speed, IF star will be negative. IT star depends upon the operating torque upon some constant K1 lambda AF. So IT star and IF star will be generated. So once if you have IT star and IF star, the IF star and IT star are helpful to determine your stator current component, the stator current component IS star. And also you can easily calculate delta star. Delta star is the angle between tan inverse of IT upon IF. So based upon this delta and IS, you can synthesize the stator currents into IA, IB, IC. So once if you have IA star, IB star and IC star, then you can develop hysteresis control. That means you can IA star, IBS star, ICS star were there. IAS, IBS, ICS were simply sensed with the help of current sensors which were going to the motor terminals. As IAS, IBS, ICS were known and IAS star, IBS star, ICS star were known, you can generally develop the gate pulses which were used to drive your inverter. So here the complete control strategy will depends upon generation of IT star, IF star. From the IT star, IF star, you have to generate IS star, and then the next one is a predictive current control of PMSM. So this predictive current control of PMSM was a new and advanced topic. So this I will show you with both with theory as well as simulation. So in the previous slides, we have seen that the stator currents are sensed with the help of sensors, and the currents, the reference currents were generated. The reference currents were generated with the help of some magnitude and angle synthesizer, and here you are generating the stator currents. The reference stator currents you are generating, and you are measuring the stator currents, and then you are directly giving to the inverter. Now this strategy of FOC was changed to predictive strategy. That means here what we are going to do is, here we will control both the inverter. We will control the inverter. The inverter will deliver the output voltage, which changes its magnitude of voltage as well as the frequency. So if I want to operate the motor, for example, if my base speed is 1500 RPM and the poles of the machine are 4, then the inverter should deliver the frequency of 50 Hz. And similarly, if I want to run the motor at 1750 RPM, then obviously the poles of the machine are fixed. I can have only the variable as a frequency, so I need to change the input voltage frequency. So the input voltage frequency simply varied so that you can get the PMSM at the desired speed. And similar way, you can decrease the speed if you want to operate at 1000 RPM. So the 1000 RPM may corresponds to 25 Hz. So you will operate the inverter with a frequency of 25 Hz. That means the modulating waveform, whatever you are going to generate, will be have 25 Hz. So in case of the predictive current control of PMSM, we require 4 major steps. First step is the estimation of the stator flux and torque. So torque has to be estimated and stator flux has to be estimated. So these two are the basic estimations. In order to estimate the stator flux and torque, you do not require much complex equations. The basic equations, whatever I have told during the mathematical model of the PMSM, psi ds is nothing but LD ID plus IFR, psi q is LQ IQR. So this ID IQ are nothing but which were obtained from IA IB IC. IA IB IC are simply measured by the current sensors. So if you have the current sensors and the rotor angle, you know the rotor angle theta r is known. If you know theta r, you can have omega r. So with the help of omega r and IA IB IC, you can easily generate the Park transformation matrix IQSR and IDSR. So IQS star and ITS star are the reference currents. These reference currents are given to the cost function. And these reference currents are generally, here I am not going through all the phenomena, how these reference currents were generated. This IAS star, IBS star, ICS star are generated through these phenomena. So this is used to generate IAS star, IBS star, IDS, ICS star, and then these are converted into ID star and IQ star. So I'm directly going for this conversion. That means here I'm only showing the outer torque loop, inner current control loop I'm not showing, and here I'm directly assuming that ID star is 0 and IQ star is only present. So I want to operate the motor below the base speed, not above the base speed. So as ID star is 0, as ID star is 0 means I do not have I have only IS component in terms of torque producing component. The flux producing component is I'm not controlling. The flux is generally it is direct rotor flux only. It is a constant rotor flux only. So in this case, IDS star is I maintained as 0, and also the maintaining of ID equal to 0 will operate the motor at good power factor. So at higher power factors. So ID star and IQ star are generated from your IA, IB, IC. IIBIC star. And the second step is you require a prediction of stator currents. So prediction of stator currents, that means IDS K plus 1, IQS K plus 1 is required. So I will just go to the simulation diagram here. Yeah. So I just told about these 3 blocks. This is the inverter block. This is a ABC to DQ block. And this DQ block is used to generate the required currents and flux components for the torque estimation. And then here it is a inverter model. So here I will show you that mathematical logic behind the generation of the code. So in the predictive current control, the name itself indicates the prediction of currents. So you are going to predict the stator currents, IDS K plus 1 and IQS K plus 1. In order to predict IDS K plus 1 and IQS K plus 1, you require the rate of change of current equation, because di by dt is known to you. Then with the help of di by dt, by using the forward Euler method, you can easily trace them. Di by dt can be written as I of k plus 1 minus I of k by ts. So if di by dt is known to you, the di by dt can be estimated from the flux equation. So you know the voltage can be written as in terms of flux as L di by dt simply. As you know, inductance V is equal to, simply if you neglect the stator drop, V is equal to L into di by dt plus omega into psi q or psi d. That depends upon your transformation and also d or q axis voltages. So if you have voltage equation, the voltage equation can be written in terms of L into di by dt. So V upon L will give you simply di by dt with respect to q axis or d axis. So that di by dt will be equated as I of k plus 1 minus I of k by ts. And from that, you can write the predicted stator current is k plus 1. So here we are using a simple equation. It is a modified equation here, this is k plus 1. And if I k plus 1 and this is a psi k plus 1, that means fs p1. So in case of the MATLAB simulation, we cannot show you the symbols. That's why fs p1 indicates the predicted flux. Is p1 indicates the predicted current. Yeah, it is. Yeah, here. This is IDS star and IQS. This is a IDS measured and IQS from the rotor. So let me show you from here. Yeah, here I have VDS VQS. Yeah, these are IDS IQS. I will generate from the motor because the motor is already in. When you are doing simulation, it is an advantage. But when you are doing the hardware, you have to generate ID IQ signals through the current measurements and the motor equations. So when you are using the hardware, it will be a different scenario. So ID IQ are the motor currents and IQ reference will be from the torque reference value. Torque reference, I'm directly generating the IQ reference. So I will show the internal logic. So these all are the machine parameters. V1 to V8 indicates the stator voltages. So these are the mathematical equations, VD equation, VQ equation. So with the help of VD and VQ, this is the equation for ID and it is equation for IQ. So ID IQ. So this ID IQ equations are generated from your mathematical model. Yeah, with the help of IAIB you can generate ID IQ, or with the help of VDVQ also you can write the equations of VDVQ equations. So you have ID's IQ equations, you can substitute them into P's IDS, P's IQS. So if you substitute here, you can have directly the di by dt equation. So what I'm saying here is, in case of the predictive current control or predictive torque control, suppose if I say predictive current control, in case of model predictive control, I require formulation of the cost function. The cost function is to operate the motor in the optimal condition. So the optimal condition is nothing but the errors or the functions used in your cost function. So in the predictive current control cost function, I'm using the current error in terms of d axis and q axis. So I have IQ and ID which were generated from motor. That means the actual currents existing in the motor. IQ star and ID star which were required by the user. IQ star is a required torque of the user, and ID star is whether he want to use the motor in the flux weakening mode or base speed mode. So here I'm showing only for the base speed mode. I'm not showing for the flux weakening mode. So it is generally we use in the laboratory. So from the equations of VDVQ, ID's IQ, you can easily write. Suppose if you place this ID equation here, then you have the equation of P into LD, where P stands for here d by dt operator, differential operator. So VD is equal to RDID. This is a drop. P is ID in terms of inductive voltage, that is LDI by dt only. So this is actual equation because I have the rotor flux now. So you have to incorporate the rotor flux into the voltage equation. That is why I am showing XIDS as LDID plus IFR and XIQ as LQIQS. So on substituting these two equations into this VDS VQS, you can have di by dt equation. If you have di by dt, you can write Ik plus 1 easily. If Ik plus 1 is known, then you can write Ik plus 2 easily. That is called as one step ahead algorithm. So here we are showing only for the simple one step ahead. That means ik plus 1 only. So the stator currents are predicted. That means isk plus 1 and idk plus 1 and iqk plus 1 are predicted by using the voltage equations. And here v underscore 01 stands for all voltage vector combinations. So v underscore 01 is equal to v of I, where v of I is equal to v1 to v7. V1 to V7 or all 8 voltage vector combinations. This I don't I don't want to go back again. So yeah, not here. This one. Yeah. So VDC, SA into SB, SC. So SA, SB, SC are the switching states of the inverter. Switching states are 2, and I have 3 legs. So 3 legs, that means A phase, B phase, and C phase. The A phase have the switching combination 1 0. B phase will have switching combination 1 0. C phase will have switching combination 1 0. So I have either 0 level or 1 level, and 3 phases were there. So the possible combinations are 2 power 3. So I am going to get 8 different output voltage levels or 8 different output voltage combinations. The different output voltage combinations are will forms an hexagon that I'm not showing. I'm not going through that derivation again. So I just given you an insight of how to generate ik plus 1 simply. So here it is a kth state value. Ik plus 1 will be estimated by using the di by dt of equation from the stator voltage values. So once if you have ik plus 1, that is in terms of d value and q value, then this idk plus 1 and iqk plus 1 will be compared with the reference values. So I will show you with the program. So here I have generated idk plus 1 and iqk plus 1. So if once you have idk plus 1 and iqk plus 1, as id reference I considered as 0, so I'm just writing idp1 square, iq reference minus iqp1 whole square. So here you can see absolute value of iq reference minus iqp1 whole square. So this is what called as cost function. The cost function is comprising of the reduction of ripple in the flux current component and the torque current component. IQ is called as torque current component and ID is called as a flux current component. This is nothing but IS will always have some angle. So IS can be decomposed into direct axis and quadrature axis. IS is nothing but your stator current. The stator current will be fed from your voltage source inverter. So here I am showing you this stator current. This is your IAIB. This IAIB is converted into alpha beta and then multiplied with e power j theta r, so that you are going to have the measured value of I of k. So once if you have I of k, you can easily get I of k plus 1, IQ of k plus 1. And this I of k plus 1 and IQ of k plus 1 are compared with the reference currents. So as I told, the PCC of PMSM implementation requires 4 steps. The first step is estimation of the flux and estimation of the currents. That means estimation of the flux and estimation of the currents. The second step is comparison of the reference values of currents with actual value currents. The third step is optimization of the cost function. So the cost function will be evaluated for all the switching combinations of the inverter. So here Vs of k indicates the output voltage V alpha, V beta. So generally the Vs of k is written by 2 by 3 VDC into SA plus SB into e power j2 pi by 3 plus SC into e power 4 j4 pi by 3. So that is a classical equation of the stator voltage which was obtained from the inverter. So usually you are writing VA, VB, VC, na? That VA, VB, VC, like I will just simply say, for example, if you have positive sequence components, VA, VB, VC. So VA, VB, VC is nothing but if you have VA component, VA will be represented with its magnitude at an angle 0. VB will be represented with VP Vp at an angle minus 120. That means if I say Vp is a voltage of the phase, so V at an angle minus 120 and Vc will be voltage at an angle minus 240. So if you have that, then you can sum up Va plus Vb plus Vc as, if you sum up Va plus Vb plus Vc, then you are going to have 0. But in case of the inverter configuration, in the sequence components, you are having a continuous waveform, which was 1 at an angle 120, 1 at an angle 240 you have. So you are going to have Vp into 1 plus lambda square. The value of 1 plus lambda square will be equal to 0. But in case of the inverter, you are going to have different switching combinations. These are all discrete instants. So 2 by 3 VDC into SA plus SB into e power j2 pi by 3 plus SC into e power j4 pi by 3. The values of SA, SB, SC are 8 different combinations. 0002, 111. 8 different combinations were there. So with the help of those 8 combinations, you are going to generate the output voltage of the inverter, and those 7 combinations are used to evaluate your cost function. So IQ star and ID star are known. IDK plus 1, IQK plus 1 consists of 7 different values. I will show you from the program. So IDK plus 1, IQK plus 1 is function of VD and VQ. VD and VQ are function of V underscore 01. V underscore 01 is having V of I. That means 7 combinations I have considered. I have neglected 111 or 000. Any one combination only I have. Okay. It was there. Okay. 1 to 8 was there. Yeah, V8 is 0, V7 is 0. Yes, both null combinations were considered. So IDK plus 1 and IQK plus 1 will have 7 values, and those 7 values are compared with your reference. And whenever the value of this error, the ID star minus ID or IQ star minus IQ are less, then the G will send an output which is corresponds to your the switching combination. That means G will be evaluated for all combinations. Whenever the value of G is less, that value of, for example, IDS has been evaluated for ID1, ID2, ID3, and so on, ID8. So for the combination of third combination, let me say. So the third combination here in the program, I have taken as the third combination as 110. So this 110 is a minimum switching combination. That means by applying 110, I'm getting the minimum value of G at that instant. So that 110 is applied to your voltage source inverter, and that inverter will deliver voltage to your PMSM. So that's all. So this is your PCC of PMSM. So it is an extended version of FOC. So here I'm replacing this inverter and control logic with predictive current control. So these all together, and in addition to this, I'm having this additional logic. And for the simplicity purpose, I am using ID star is equal to 0, and I have only the stator current as IQ component. And the motor will operate less than the base speed. Okay, so this is about how you can develop the predictive current control through the simulation. And after doing the simulation, this is a response of the motor. The speed was changed from 300 RPM to 800 RPM, 1300 RPM. And the motor flux is at 0.701. The torque is as shown here, and the motor was not loaded in this condition. So these are the simulation result which was obtained by using the PCC, and these are the experimental results. And the right part is during the no loaded condition, the torque is always at ground level, that means 0 level, and the green color indicates the speed, 300 RPM per division. So the different speeds were shown, 300, 800, and 1300 RPM were shown here, and also the corresponding the flux lambda is 0.1 Weber per division. This one lambda is okay. So and the second side, this side. So here I have applied a sudden speed changes from 300 to 800, 800 to 1300, and the dynamic response was shown here. So you can see here the dynamic response. A low torque of 0 to, yeah, here also you can see the dynamic response. For the time scale is 1 second. So 1 division stands for 1 second. So you can observe here, the motor reached to steady state lesser than 0.5 second. Okay. So I have applied a 500 RPM change. That means I can say in the physical mode. So you are running at 10 kilometer per hour and you can suddenly switch over to 80 kilometer per hour in a very short span of time. So that is possible with the help of PMSM, and that to be predictive control. PMSM with predictive current control. And that sudden torque change. So the like here initially motor is running at no load condition. Suddenly the motor was subjected to a load torque of 5 Newton meter per division. The rated torque is only 10. Here we are applying half of the rated torque. So on even applying half of the rated torque, the motor has came back to its normal condition just after 0.5 seconds, less than half second. And this is a stator current, IS component, IS stator current, A phase current component. Here it was shown IA. So A phase current, and the one division is 2 ampere per division. So the motor is around 4 ampere. So 4 ampere means I might have a rated peak current of around 4 into 1.732. So that means around 5.2 something I will get. So for half of the rated load, I'm having only 3.2 as a rated current, 3.2 as a peak current. Okay, so these are all the basic things of predictive current control. Now I will move to the predictive torque control. Before going to predictive torque control, the other fundamental thing is direct torque control of PMSM. So in case of the predictive current control, as I told you, it is the extended version of field oriented control. So the predictive torque control is an extended version of direct torque control. So after this completion, I will go to the PTC, and then I will show you direct simulation of PTC and PCC separately. So in case of predictive torque control, as I told, the voltage giving to the motor can control torque and flux component. So here the two equations were shown, d psi by dt equal to V minus IR. Let me say this IR is drop is negligible. So if IR is negligible, then d psi by dt is nothing but stator voltage. This voltage is nothing but the output voltage of the inverter. So if I control the inverter voltage, I can have the flux control. And also if I move the voltage at a value, at a very higher value, and the rotor dynamics, that means the rotor is mechanical, and also rotor mechanical time constant of the rotor is much higher compared to the electrical time constant. So during one short sample of interval, the rotor flux will be constant. So if the rotor flux is constant, the value of IS and IR, the angle between the IS and I can say lambda f. So the angle between IS and lambda f can be changed very quickly by changing the stator voltage angle. So by applying the stator voltage in intervals of time, that means if I apply voltage vectors from V0 to V8, V0 will be at 0, V1 will be at 0 degree, V2 60 degree, V3 120. Like that, I will have the 6 voltage vectors are aparted by 120 apart by 60 degree. So here one illustration was shown here. Initially, the stator flux is at this point. So d psi by dt equal to Vs. I'm neglecting this RSIS drop. So this change is d psi is equal to Vs into delta t. So if I apply the voltage vector for Ts interval, I can change psi s to psi s plus t. That means psi s of t plus Ts. And the rotor flux is assumed to be constant. The angle between psi s and psi r is assumed to be theta sr. So now initially the angle between psi s and psi r, that means psi s is proportional to Is, I can say. The psi r is a rotor flux. So initially the angle between the stator flux and rotor flux is theta sr. On sudden application of the voltage vector, the psi s was moved from psi s of t to psi s of t plus ts, and also the angle was changed from theta sr of t to theta sr of t plus ts. So by applying the voltage vector for certain interval of time, that means sample time, ts is a sampling time. So by applying the voltage vector for this interval of duration, you can change the flux of the motor as well as torque of the motor directly. So the direct torque control is a simple phenomena. The application of the voltage vector will change the torque and flux dynamically. And the flux equation is given by root of lambda d square plus lambda qs square, and theta s is here. What are this theta s? I'm saying theta s is equal to tan inverse of lambda q by lambda d. So these are the two equations used to calculate the lambda s and theta s, which were required for the implementation of the sector. So here I have assumed that the voltage Vs was applied like this and change of theta s and theta r. So here theta s was changed from theta s of t to theta s of t plus ts by applying this voltage vector of less than 90 degree. So if you apply the voltage vector more than 90 degree, that means here psi s and voltage vector you applied more than 90 degree, then instead of increasing the value of torque, the torque will start decreasing. So that will be possible in the deceleration operation. So you will have acceleration operation, that means increasing torque and the decreasing of the torque. So we are going to apply the voltage vectors in the clockwise, V1, V2, V3, V4, V5, V6 for the increasing of torque as well as increasing of the flux. And if you want to decrease of the torque and decrease of the flux, you are going to operate the motor in the reverse direction, V2 and then V1 and then V5 and then V4. So you have to go in the reverse way. So I will show you that voltage vectors here. So V1, V2, V3, V4, V5, V6 are the voltage vectors generated by the inverter, and the sector 1 is from minus 30 to 30, 30 to 90 is the sector 2, 90 to 150 is sector 3, 150 to 27 less than 270, that means around 240 will be sector 4. So in this way I am defining the sector for every 60 degrees. Here it was shown here. So I told that lambda psi s. So I told with one voltage vector. Now I will tell you psi s, the application of Vs. So if you apply the voltage vector V2, so on applying the voltage vector V2, there will be increment of the flux as well as increment of the torque. Okay. So initially you have theta s. Now theta s r will change to here. And if you apply V1, on applying V1, you can increase the flux to a higher value, but it will decrease the angle, so the torque will decrease. So if you are in sector 1, by applying the voltage vector V2, you can increase both flux and torque. And by applying the voltage vector V5, you can decrease the torque and flux. So it is assumed, that means here I am assuming that the psi s is in sector 1 and I am applying these voltage vectors. And similarly, if the stator flux, that means for one complete rotation, the stator flux will make 0 to 360 degree. So it will go through the all sectors. In all the sectors, the application of the voltage vectors were shown. So if you want to increase the flux to increment or decrement, I was shown here 1 and minus 1. So to increase the flux and torque, you have to apply the voltage sequence V2, V3, V4, V5, V6 in the clockwise. If you want to decrease the torque and if you want to decrease the flux, you have to go in the reverse direction, V5, V6, V1, V2, V3, V4. Okay, so this is how you can generate the lookup table. This is a lookup table which was much important in case of direct torque control. So if you skip any one of the voltage vector in a wrong way, then you are going to get deteriorated performance. The motor will operate, but you cannot get the response properly. So from this slide, I want to tell a simple thing that by applying one voltage vector, I can change both the value of flux and torque. So one shot, I'm going to have two boards. Here, so omega r star and omega r is compared, and the reference torque T star will be generated. And this psi s star will be generated depending upon the operating speed of the motor. So if you are operating less than base speed, the psi s star will be a constant. If you are operating more than base speed, the psi s star will be a decaying value. The psi s star will be compared with the psi s, and here you are going to have the flux error, and here you are going to have the torque error. So the torque error and flux error, from the output of this torque error and flux error, you are going to get the values ht is 1 or the you are going to give it to a hysteresis band. The hysteresis band generally is chosen as a, for example, in case of torque hysteresis controller, usual range of the torque band will be 3% to 5%, not more than 5%. Suppose if I have rated torque of 25 Newton meter, the maximum torque band, the maximum hysteresis torque band chosen will be around 5% of 25 means 1.25. So I can choose 1.25 and minus 1.25 and 0 as my torque hysteresis band, and the flux hysteresis bands are 1 and minus 1, and generally the hysteresis bands of the flux will be chosen as less than 0.5% of rated flux. Less than 0.5%, that means 0.5% of rated flux, I can say. And the sector information. So I told you here, the voltage vector will be chosen depending upon the flux error, torque error, and the sector. So the actual flux and reference flux were given to the flux hysteresis. It will generate H psi as 1 or minus 1. HT will be 1, 0 or minus 1. Theta S, the theta S will be 1 to 6. 1 to 6. So if theta is minus 6, minus 32 plus 30, it is 1. If it is 30 to 90, sector 2, 90 to 150, sector 3, like that I define. So based upon the sector information, I'm generating the sectors 1 to 6, and depending upon HT, H psi, that means HT is 1, 0, minus 1, or H psi is 1 and minus 1, and theta is information 1 to 6. You are going to develop the lookup table, and the lookup table will give you the corresponding voltage vector. The voltage vector, if I say, yeah, here it is a, yeah, if it is V2, the corresponding switching combination will be 110. V1 100, 110, 010, 011, like this, 001, 010. So like this, you have the six switching combinations here, and the corresponding the switching vector will be given to the inverter from your voltage vector selection table, and that drives your inverter and gives that voltage vector to the motor drive. So it is a continuous process. And here, in order to estimate the flux, in order to estimate the torque, you require a mathematical model. The mathematical model VdVq, IdIq, you are going to generate from the ABC to DQ transformation or ABC to alpha beta transformation. So if you have the PMSM, if you have done the mathematical model of PMSM in the rotor reference frame, then here you are going to generate directly IdIq, VdVq. But if you have developed PMSM model in stationary reference frame, then you have to get you are going to get I alpha I beta, V alpha V beta, and then you have to convert it into VdVq or IdIq or based upon the required thing. So mostly in case of DTC, we require stationary reference frame only, whereas in case of the FOC, we require the rotor angle and all the currents are synchronized into rotor angle. And the second thing, it is very easy to implement than FOC, and it does not require any current loop. It requires just outer torque loop and the flux loop. So it is about the direct torque control simulation diagram. And I told you the hysteresis band delta T and delta lambda. This delta T and delta lambda will be 3% or 5% of the rated torque and less than 0.5% of rated flux. So this is a simulation diagram. This is a simulation response and experimental response of a direct torque control. So here I applied sudden change of 200 to minus 200. So in the simulation, you can see 0.15 second is required. 0.15 second is required to change from 200 radians per second to minus 200 radians per second. And yeah, here I'm mentioning in terms of radians per second. So 1 radians per second is equal to approximately 10 RPM. I'm not showing the mathematical calculation. So 314 radians per second equal to 1500 RPM. So similarly, 200 radians per second is approximately 1000 RPM. So 1000 RPM to minus 1000 RPM, I'm moving in less than half second. So that is what will happen in case of FOC or DTC by using PMSM. So you can get that much faster dynamic response by using the PMSM as well as the good control strategy. So it is a direct torque control, and the experimental response also you can observe here. In 1 second, the fast response can be obtained. So 100 to 200 radians per second 200 to 300 radians per second. So the physical motor offers higher amount of inertia. Due to the higher amount of inertia, it will require some time for the settling. That settling will be less than 1 second. And the second thing also, it depends upon the tuning of PI parameters, the KP and KI gains also. So this is the response of PMSM with the DTC. And the limitations of DTC are the information of sector flex, space phasor is required, trigonometric calculations are required, and the classification of sectors is required. So in order to abate these limitations, predictive torque control is one of the alternate. It is a combination DTC of PMSM is same as DTC only. So it requires 5 different steps. First one, identify the measurable variables, estimate the variables. Yeah, I told you estimation of flux and current, and then predict, and then formulate cost function, evaluate estimates. So you have to understand what will be the estimates, what will be the measurements, what will be the predictions. So in case of motor applications or even the inverter applications, for the motor drive applications, let me say the speed, current, and voltages are measurable. So if DC voltage is measurable, then you can easily trace V1, V2, V3, and so on, and estimates. You are going to estimate the stator flux and rotor flux, and you are going to predict the flux and torque. So once the prediction of torque and flux were done, then you are going to formulate the cost function. So let me show you the code here. Yeah, you can see here. It is a reference flux 0.705, reference torque. Okay. So the reference torque and reference flux were obtained from the external things. And here I am estimating the flux, XISP1. And this is a prediction. ISP1 and XISP1 are predictions. And the other thing, here dq to alpha beta, yes, bdvq, yes. Here this q, xid and xiq are the estimates. Xid, xiq are the stator flux estimates. The stator flux estimates are or else here also you can estimate here. Xis equal to Ts into V minus IAR. So this is a d psi by dt. So from that you can easily get Xis k plus 1. D psi by dt equal to xi k plus 1 minus ik by ts. So with the help of that, you are estimating the stator flux. And if you have FSP1 and also ISP1, you can generate the torque prediction. So once if you have the torque prediction, then I am writing the cost function. G1 is for the torque ripple, G2 is for the flux ripple. So the sum of this G1 and G2 will be used in the cost function. So here I am multiplying the 75. This 75 is a weighting factor. So I will go to the seminar. Here. So in motor applications, first you have to identify the measurements: speed, current, DC bus voltage, estimates, stator flux and rotor flux, and the predictions, flux and torque, and the cost function, flux error and torque error, and the minimize the cost function to get the optimal voltage vector. So here the block diagram was shown, part of the block diagram. It is not the complete block diagram. So from the rotor, I'm measuring the speed and given as a feedback, and I'm estimating the flux and currents for the next state. So with the help of psi k plus 1 and I k plus 1, I'm estimating the torque. So t k plus 1 and psi k plus 1 are given to the cost function. The cost function will comprise of the minimization of the torque ripple and flux ripple. So the basic ideas are the use of model to predict the future behavior of the variables, a cost function that represents the desired behavior. The optimal actuation is obtained by the minimizing the cost function. So this is a PMSM model in discrete domain, which was used for the implementation of the PTC, what I have shown. Yeah, in order to do the predictive model, I'm showing the Euler equation. This is a predictive model, dy by dt. And the detailed analysis was shown here. IQ k plus 1 is psi q k plus 1 by LQ. Yeah, once if you have d psi by dt, then you can have xi d k plus 1, xi q k plus 1. by using this equation. By using this equation, you are going to have psi dk plus 1, psi qk plus 1. If you have psi dk plus 1 and psi qk plus 1, you can easily have iqk plus 1 and idk plus 1. So psi dk plus 1 into iqk plus 1 minus idk plus 1 into psi qk plus 1 into 3 by 2 p by 2 will give you torque k plus 1. That means torque in the next state. So step 1, estimation of stator flux and stator voltage and currents, estimation of stator currents and flux linkages, and then yeah, here I have written in terms of just estimation, like everything you are going to have in the prediction algorithm. That means in the program I am writing, that's why I have written as estimation. So these all were written in the program. Estimation of torque and flux linkage from stator currents, and then estimation of, that is prediction of torque and torque error, that is delta TE. This is what I have written as G1 cost function. This is a G2 cost function, and selection of cost function which is obtained from the addition of these two cost functions. So G1 is T reference minus TK plus 1. G2 is F reference minus psi reference minus psi K plus 1. And when compared with the torque, the flux is a very small value. And I already told you torque will be in terms of Newton meter, 25 Newton meter, whereas flux in terms of 0.7 or 0.0, 0.5 or 0.7. So both are dissimilar quantities. So the addition of weighting factor is necessary in the cost function. Whereas in case of the currents, IQK plus 1 and IDK plus 1, both are current terms. So there you need not to add any weighting factor. So this weighting factor plays very important role in the implementation of predictive torque control. So this is about the cost function, and this cost function will be evaluated for all the switching combinations. And this is a simulation and experimental study of PTC of PMSM. So here you can see the top results are the simulation and the bottom are the hardware results. Yeah, the simulation results, we have taken the inertia constant as a very lesser value, and also the simulation will does not depends upon all the parameters of the real-time parameters. Whereas in case of experimentation, all parameters will present, so you cannot get exactly as a simulation result. But the dynamic response will depends upon simply the inertia only. So if I change the inertia, then here also I can show you with the same response as in the experimental results. So here results were shown for the various speeds of operation of the PMSM in all the conditions. And we have also made a comparison between PTC and DTC SVM. This DTC SVM I'm not able to discuss. And the other techniques also there, like sliding mode control, MRAS control, and also many additional control techniques were there. So here I have discussed only the predictive control in terms of FOC and DTC. And these are the PMSM has found in applications, very important applications, EV, machine tools, servo drives, etc. And it is also used in washing machine or washing dryer application. And here I'm just making a comparison between induction motor and PMSM. The efficiency of PMSM is generally high. Power factor is also high because it does not require any magnetizing current for the flux generation. Dynamic response is faster compared to induction motor, and also the speed range. It is easily for higher speed can be easily obtained by simply changing the stator current, whereas in induction motor it is very difficult. The overloading capability was better in case of PMSM. The torque is also smooth in case of PMSM. So due to these advantages, the PMSM is also suitable for medium power as well as high power applications for EV applications. And this is a one slide which shows where the R&D is required for the electric vehicles. So inside the vehicle, we usually work on energy storage, energy management, power electronic combinations, motor drives, and in the motor drives there is huge amount of research can be done. And partially inside the vehicle, on-board diagnosis, that means faults, autonomous vehicles, that means to make the vehicle to run by its own. And then cyber security applications, that means autonomous vehicles are done with the help of state estimation and artificial intelligence. And the outside vehicle, I told you, V2G systems, fast charging stations, V2I, vehicle to vehicle interface or vehicle to grid interface communications, IoT based interfacings, or smart grid systems. So This is broad research and development can be done in the electric vehicles. So you can choose your own topic and you can work in that respective topic for your research. So as as an electronic engineer, as an electrical engineer, I work in the first side inside the vehicle. That means energy storage, management, or electronics, motor drives. So mostly in the coming days, we are going to develop a complete strategy of energy management, power electronic, as well as a motor control with a single controller in our lab. Yeah. So whatever I have told you, so that is what I have listed here. And the limitations of battery electric vehicles are the poor efficiency, low power density of the batteries, short life cycle of the battery, lower operating range of the batteries, and batteries are not designed to provide bursts of power whenever it is required. That means hundreds and thousands of the drive cycles. That means accelerations or decelerations or long duration of the run is required. The time battery will be a very difficult task. And in urban drive, we require frequent acceleration and deceleration. And in the internet, there will be one cycle called as urban duty drive cycle. So you can download the urban duty drive cycle and you can verify your simulation is meeting the requirement of EV or not. So in our laboratory, after developing complete experimental setup, we'll run the motor with that UDDC cycle, urban duty drive cycle, for more than 3 hours. More than 3 hours, we will verify. That means the motor will operate at the speed of 5 RPM also. That means around the zero speed. Around the zero speed also we will test. That means, I told you the examples of low traffic condition. In the low traffic condition, you have to run around 10 RPM or 20 RPM. In the 10 RPM or 20 RPM also, your motor should able to give better response. So that is what we will do in the laboratory with the same control strategies, not the other control strategies. We will use the same control strategies, but we are going to add some novelties in the control. That's all. The more focus can be developed in the R&D or also startups and also Make in India will help uh, to have EVs on the road in the short span. So if you have any questions, you can ask me. Now the session is open for you.
Dear participants, if you have any discussions regarding this session, discuss with Praveen Kumar sir. Thank you, Dr. K.P. Praveen Kumar sir, for your valuable insights in this session.
Yeah. Yeah, thank you all. I think many of the faculty were there so that they can easily understand the both. I have gone through the simulation also parallelly because I want to make real understanding of how you are developing what I'm saying and in the MATLAB. So that's why I have shown. The same will be developed in the experimental setup by using the codings. That's all. So if you have a microcontroller, right now I'm simply giving you two controllers like 28379D, which is much suitable for the motor drives. And the second thing is STM microcontrollers. In the Amazon also it is available for 3,000 rupees. So if anyone is interested in the motor drives, they can do their own development of their laboratory in their home with a very cheaper cost, less than 25,000. The controller will not much costlier. IGBTs are not costlier. IGBT you require 6 IGBTs, and the capacitors will be less than 1,500 rupees. So if you want to develop your own setup, it will be very easy, and you can verify your simulations at your home itself. For any assistance in your hardware development or any other things like simulation also, you can contact us. So if any other questions are there, you can ask me. Or if anyone, if any of your MTech students are interested to do PhD, you can suggest us. We have a well-established laboratory in SVNIT Surat. And if you are interested, you can visit our laboratory. Yeah, thank you all. Yeah, I'm leaving the meeting. Thank you all.